It has connected. Good evening, everybody. Good evening.
Good evening, sir.
Good evening. Sorry,
Good
a
evening, sir.
little bit late. Good evening. And let's just start immediately. I was trying to connect. I was having problem with connection here. Yes, I'm connected now. I think we start immediately because this is 30 minutes after.
Yeah, good evening, sir.
Good evening, sir. Yes, sir. Yes, today we, 2 days ago we discussed the relationship between probability and statistics. So we'll continue the discussion, but we're looking at discrete probability distribution. We rounded up our discussion 2 days ago by talking about probability distribution. So we'll quickly go over what the last thing I said about probability distribution and the type of probability distribution, and now go down on discrete probability distribution. We said that the probability distribution is the list of all the probabilities of different outcomes, or the list of all the different outcomes of a variable and their probabilities. So if you say, okay, a variable like marital status is a variable, and the different outcome, a different value are single, married, divorced, separated, widow. So all those 5 options, what are their probabilities? So when you list the different outcome options, which only one can happen per time for a person. So, and the different probabilities for each option. That is the probability distribution for marital status. And when you add all those probabilities together, it should be equal to 1. So none of the probability can be less than 0, none can be greater than 1. In fact, the addition of all of them will be 1. So when we talk about probability, that's just the concept. But now we want to quickly look at the different type of probability distribution. There are many types, but they can be grouped under 2 categories, which are discrete and continuous. Discrete and continuous. Once you remember our classification of variable into discrete and continuous variables. So the discrete probability distribution is probability distribution for discrete variable. Continuous probability distribution is probability distribution for continuous variable. What are these discrete variables? Variable that you have limit, you can know all the possible outcomes. For example, sex, marital status. Think of anything categorical that you can know all the possible outcomes. It can be numerical, but in this case, it has no it has no decimal. Like if you say number of time, rate or something, a number of children, number of people, you cannot say 2.5, 23.5, it's whole number. When you are dealing with whole number, it's a form of discrete variable. Or if it is categorical variable on its own, like sex, like marital status, like any, whether ordinal or nominal variable, to find its categorical variable, they all follow discrete probability distribution. They are example of discrete variable. So the meaning of discrete is that you can actually have distinct category. Yes, distinct category. Say this are, even if you say that if something says okay, the number maybe 200, if you say 200 people attended a particular occasion, 200 is 200. There's nothing like 200.5. It's whole number. It's a form of discrete variable in the sense that it doesn't have decimal. You can say 200 is 200. In between 200 and 100, you can count the number, possible value, 100. The difference will be 100. Between 10 and 5, you can see there are 5. Unlike continuous probability distribution or continuous variable where you don't even know, there's no, you cannot say you know all the possible outcomes. Like for example, how many possible blood sugar can you have or blood pressure? So anything that can have decimal, they are continuous variable and they can follow continuous probability distribution. Whatever can have decimal. So like for example now, if you talk about blood sugar, between 65 and 60, you cannot say it's 5 now. No, even between 60 and 61, you can have 60.009, 60.07, infinity. So when you have infinity number of possible outcomes, possible values in between two given values, that is a form of continuous variable. It's followed continuous probability distribution. So if you just look at that. Now, just to draw us back, for us to be able to conceptualize. I said yesterday that what happened in the realm of idea is what is in the population, the phenomenon you are studying, the characteristics you are studying, the distribution just means the pattern of occurrence of this characteristic. It's actually a probability distribution because each of the outcome has its own probability. That is the value, because the value vary. Some are common than the other. A particular value may see in the population, female may be more than male, male may be more than female. We're talking of marital status, married may be more than single and divorced, or maybe single and more. And you know that single and more are single and married are more than separated and divorced or widow. Because those are the different possible outcomes. And the one that are more will probably have more the probability will be higher. That is, the percentage of people under that category will be higher. That shows that the probability, if you select somebody at random, the probability of that person being single or married will be higher than that of widow or separated. That's what it means. So in the population, so that is why probability theory is what tries to give model what is in the population. But when you now take sample, you just take some of the population and now examine them, is statistic that will help you summarize. Can you see? It's statistics that help you summarize that, now try to make projection through the statistics about the population. But the probability give you the model, give you the idea, theorize, give you the theory behind it and why, and statistic examine it. When the statistics now examine it, the distribution is giving is still probability distribution because what statistics explaining is just a picture of what is in the population. It's just explaining population based on the sample you have taken. So that is why when you bring your result on the table, or you plot graph or whatever, or write equation based on this sample you have taken, what you are showing is probability distribution also. So it can be in form of table. When you put your variable on the table and put the percentage there, and you make sure you sum the percentage over 100%, you show the relative frequency. It's probability distribution. It's only that some are discrete, some are continuous. You cannot show continuous probability distribution on the table. It's not possible because on the table you are trying to say, oh, these are the possible outcome, and you show their probability. It can only happen with discrete because it's only the discrete you can say we have social category. In a situation where you have continuous variable, you want to show it on the table, you just have to range it. When you range it or you have a cutoff, you have changed that continuous variable into categorical variable. In that case, now you are using, once you change categorical variable, like age range, when you range here, or your blood sugar, you can say blood sugar between this and this, between this and this, or greater than this. You put it on the table. It's no more the raw blood sugar, is the range blood sugar. That one is categorical variable. It has become discrete variable by categorizing it. And that is why it is not possible to know the probability. You cannot know the probability of a given value may contain if that particular variable follow continuous probability distribution. We'll still talk about that maybe next week, because today we'll discussed extensively about discrete probability distribution. By the time we talk on the continuous probability distribution on Tuesday, we're going to see maybe the reason, though we have talked about it in the previous lecture we gave on probability and normal distribution. Extensively, many of us were not there, but if you go and watch the video, it will give you the clue, and we'll still talk about it, revisit it on Tuesday. I will advise people to subscribe, and so that you get for you to get, the more you know what happened previously, the more you get to understand our lecture very well. You just your own advice. We keep on saying that because some of the things I'm saying here, we have mention of them. So it is when you try to learn something from different angles that is stick. You have a mental picture of it. So I think you should be able to differentiate between discrete and continuous. Look at the graph here now. Look at the graph. This one is okay. Different type of probability distribution. Probability distribution of discrete variables. This one, if you look at it, 0, 1, 2, 3, is showing whole number here. And this whole number, you can see each graph is separate. So 0 is separate from 1. 1 is separate from 2. So there's gap between them. They are separate. That's why it is discrete. Even if it is male and female you are plotting, it just shows the height of the male and female. If it's marital status, you will show separately the height of the married, single, divorced, separated, or widow, separately like that. That is why it's discrete. But if it is continuous probability distribution, because there's decimal, there's room for this. That's why you see something like 80.5, something 81, 81.5. And because even between 81.5 and 80, you just use for convenience, you use 81.5, it can be 0.1, it can be point anything. So that is why there's no sharp boundary. And that is why you see the bar, they overlap. There's no gap. And that is what we call histogram. If you plot a bar like that with gap in between, that would be bar chart. It is appropriate for discrete variable because the discrete variable follow discrete probability distribution, while for continuous variable, you can only show it with histogram, where you have a bar and you have bars that there are no gaps. So this 80 just for convenience because there's no sharp boundary between 80 and 81. You can have value that's 80, 80.009, 80.00001, So there's no boundary, just whatever label they gave here, it's just for convenience. So there's no sharp boundary between different values. So that's why it's a continuous, it's a continuum. And we have different type of, they just in this graph now, 2 examples of each. For discrete, we have binomial, we have Poisson. For continuous, we have uniform, we have normal distribution. You're able to see more of the example. Now, there's something I need to say. Because, I said that you cannot show continuous probability distribution on the table. You can show it in a graph like this. You can show it in a graph. Because if you show in a table, you are telling us that, oh, this is this value, this is the percentage. It's not possible. If you should try to show it in a table, you might have changed it to discrete variable for you to show it. Just like the way you arrange your age before you can put it on a particular table. But it can be shown on a graph. And the simplest graph to show it is the we call the graph probability density function. Now, I'm trying to show probability density function of different probability distribution. So whenever you're showing probability through graph, probability density function, you can you can plug that for anyone, for even discrete or continuous. Of course, discrete, we know that you can easily show table. But for continuous, you can only show it on table, you can show it on graph. You can show all of them on graph. So we now have the graph. It's the only way we can actually show, we can show them in equation, all of them also. To give a meta picture now, it's only the graph that can actually give a meta picture of the continuous probability distribution. Whereas for this, you can show it equation, graph, and table. Now, these are probability density function of of different probability distribution. And when you plot the graph, the area under the graph is usually 100%. 100%. The area in any probability distribution, because probability can never be greater than 1, cannot be greater than 100. You know, for the people that are new in our lecture, you know, 1 and 100 is the same. So 1 means 100%. It's just a matter of multiplying by 100 or dividing by 100. 20% means 0.2. 50% means 0.1. So why the 1 you use fraction, the 100 you use percentage. So it's just a factor of 100. So if they say 55% means 0.55, 60% means 0.6. So just note that. So the area cannot be greater than 1 or cannot be greater than 100%, that is the whole. So I think when we talk about continuous probability distribution, especially on normal distribution, maybe you'll be able to have better mental picture of why it is easy to, you know, just say, okay, the graph, the whole, everything is 100 or 1. Now, I just wanted to show the shape. I want you to see the shape of the different probability distribution. This is not exhaustive, because if you look at the first statement here, is that although the space of probability, possible probability distribution function is infinite, it's unlimited. There is a handful of distribution that can be used to approximately model a wide range of problems. So we just have some. We can have as well. If you begin to list probability distribution, you 100, more than 100, BC, beta, gamma, different things. The one that is not even be useful in your situation, you see, because of course different things behave different way, and you can use more than one to model a particular situation. It may be that some may be better than the other, but we have a handful of common one that you can really use to model the common things, problem we encounter, or common variable we want to describe. We all know that there are some naturally occurring variable, social science and biological variable that follow normal distribution, like IQ, like blood sugar, like weight, like many things like that. They follow normal distribution. So now we have some other things also variable that follow that distribution. And you're going to see that the most natural among all the distribution is actually normal distribution, because the reason is very simple. Is all the distribution, they are hiding under normal distribution, because somehow, all these distribution you are seeing here can approximate normal distribution. They can change to normal distribution if some conditions are met. So some of these distribution you're going to see also will be sampling distribution. What I mean by sampling, that one, so please go and watch our video on introduction to inferential statistics. That's why we talk about sampling distribution. Okay, like now we say blood sugar, you can see you collect data about your blood sugar, about weight, about many variables, and you see maybe they follow normal distribution, or maybe follow binomial distribution or whatever, for those ones that have not follow normal distribution. But when you are talking about something like chi-square distribution, it is not those variables that actually follow chi-square. It's their sampling distribution that follow T, chi-square, and Z also. Even normal distribution also. The sampling distribution can follow normal distribution. It can follow Z, chi-square distribution, many form of distribution. What do I mean by sampling distribution? Well, if you take your sample now, the pattern of value of the variable, the variable in the data set, maybe let's say height now. So different value, you can plot it to see the way it goes. But if, let's say, you take sample 100 times, the same thing, maybe sample of 200 people, 100 times, you summarize. When you summarize, that summary also for different sample will follow a pattern. That is what I mean by sampling distribution. So in that sense, it will lead us to, don't let me go into that, central limit theorem. All these things that will not follow normal distribution, that follow all those geometry, all this one, their sampling distribution will follow normal distribution if the sample size increase. They are sampling distribution. That is, if you take their sample, and it's very simple to conceptualize, because if you talk about height in sex now, male, female, it's not a number, they are not number, it's either male, female. But when you summarize it and say, oh, sex, female is 52% female. So if you take sample many times, it will give you different value, 50, 50, 52, 53, 57, 68. So it gives you that different value will follow normal distribution, even though the original variable is not quantitative. But when you summarize it as percentage, it's quantitative. That is why the sampling distribution will follow normal distribution. So leave that one. These are the different shapes. Look at uniform, Bernoulli, binomial, hypergeometry. You see the double arrow, you are seeing that they are related in some condition. If some conditions are met, hypergeometry will become binomial. If some conditions are not met, binomial will become hypergeometry. The same to uniform and Bernoulli, Poisson, exponential, normal. Can you see? You see Poisson, see normal, hypergeometric, normal, going to normal. Normal, if you do log normal, take the logarithm. So the student state also can be normal if some conditions are met. Chi-square also can be normal if some conditions are met. Gamma, beta, can you see different? So it's just for you to see have a mental picture. Some of these are discrete, some are continuous probability distribution. We're going to see them later. Now let's quickly look at discrete probability distribution, because that is the topic of today. The different type. So these different type you see also, they're just the common one you may encounter. Let me tell you the most common you will encounter, the most important among them is binomial. Then followed by Poisson and others. So the most important, the commonest one is binomial. So this list is not exhaustive, can be made on 200 said that you can describe, but these are the common one. And what I just wanted to have mental picture of, anyway, each session I want you just to look at something. The second column is what I want you to look at. Pay attention to. We are still going to describe each of them one by one. So look at the second column here. Please be noting, be typing your question. Be typing your question and be posting it so that when we stop, you can ask your question. I can read or whatever. Now, the second column, look at the first, discrete uniform. Outcome that are equally likely. So when you have finite outcome, when we say finite, of course, we know that even for, because there's uniform also that is under continuum. This one, these three uniform. That's why they put finite. Finite means that there are limited number of outcome. Of course, if there is unlimited number of outcome, it cannot be discrete. Now, they are equally likely. That is why it's uniform. That is, different outcome will have the same probability. Different outcome have the, so that is why you see the graph there. Can you see? It's just the same level, all of them. For all the different outcomes have the same probability. That is uniform. Then binomial is a number of sources in the first trial. So in the first trial, end trial, there's a first end trial. That is, okay, if you try to toss coin 10 times, in saying that tossing coin 10 times, that is first trial. Or somebody go for a particular exam, go for a particular thing 20 times, want to see the outcome. You attend what do I call it? A particular conference every year for 10 years, consecutive years. So you are talking of fixed number of times. So, or maybe you toss a die 60 times or 100 times. So the issue there is that, or even you have a sample of 400. If you are dealing with maybe categorical variable, it's a fixed. The sample size, once you have a sample size, it's a fixed. It's fixed. It's fixed trial, because in the sample size you want to know the value of each of those variables. Is this person married? For 400, if you come, you ask, are you married or divorced or this? You ask as you have. For the one person is one trial. For another person, up to 10 people, 10 trial. If you do it for 400, that's 400 trial. You don't know that when you are collecting data, when your sample size is 400, for each of the variable you are collecting now, by asking what is your age. You don't know each of them is one trial of because you are performing an experiment. You are collecting data is one trial. Each person is one trial. So when you talk about the age now, there are on 400 trial. If your sample says 400, if the sex is a variable, there are 400 trial of the sex also. So that's what I want you to have the mental picture of what the trial means. So what this one is telling you, a number of successes in the first trial. Like for example, now you may say, if you are collecting data, if you are interested in sex, in male sex, say what proportion out of the 600 people or 400 people, what proportion are male? So the success will be the male. If you are interested, what proportion are female? The success will be the female, while the failure will be anything that is not female, which is in male. If it is even the carrier, we are talking of what do I call it? Marital status. If you are interested in marrying, the number of, out of the phone, how many are married? Success would be the married. The failure would be any other thing apart from married, either ever divorced or whatever, or single, all of them under failure. So in binomial distribution, it divides the thing into two. It divides the outcome into two. Irrespective of how many outcomes you may even have naturally. But it has divided into two. Even blood sugar. We know that if we do blood sugar, we know that unlimited number of variables. But when clinician divides, there's okay, at 126, anything 126 and above is diabetic, the rest. So the success here is the diabetic, the failure is the rest. So if you divide the outcome into two, the desired outcome you are looking for is the success. The anything outside the desired outcome is failure. That is why in binomial there are two possible outcomes, success or failure. But one thing you should know that make it differ from other discrete probability distribution is that the number of trial is fixed. Okay, the next one is like a Poisson, number of arrival in the fixed time period. Here now is what number of something in the fixed time. It's not the trial now, in the fixed time, where it can be space also, can be placed in a place. When it says it may not be time, it may be when it says space, it can be a place or time. So now we'll still talk about geometric distribution, number of arrival in the fixed time, number, I think geometric distribution, number of trial up to the first success. In geometric, can you see why geometric is different from binomial? Is that in geometric, the first success out of many trials. For example, now if somebody just stay in a garage, you want to know as the car are moving, you are looking for one, how many cars will you have counted before Lamborghini comes? So if you from 8 o'clock in the morning now you get to the car park, garage, you are just looking, somebody is counting, number is passing 1, 2, 3, 4, 5, 1,001 until you see one car is looking. So that number, number of trials before the first success it follow geometric distribution. So you know that it will be skewed. Then negative binomial, number of trials up to negative binomial, number of trials up through K success. So here now, you are looking at a number of trials. That is where it's a little bit different from geometric and binomial. Number of trials. Anyway, when we get to this section, you'll be able to understand this one better. So negative binomial now is number of trials up to K success through K success. K success is not the first success now. How many success you are looking at? Number of trials before you get those number of success. Whereas for geometry, it's the first success. Then hypergeometry, number of marked individual example taken without replacement. So where hypergeometric is different from this one is that binomial is that in binomial, You don't replace, but here there's a replacement. Anyway, let's just go through, because I just do that for you to see the table, but every other, all those equation, they're just showing you the density function. You say that it can be modeled by table, picture, and graph. Probability can be modeled by table, graph, or equation. Anyway, let's just go to town. There's someone that is not on that table, which is Bernoulli. I think it should be there. I should make mention of it because it's the simplest probability distribution. It's the basis for most of other, especially binomial. A discrete probability distribution with only one, two possible outcome and a single try, which is called Bernoulli try. Let me just put in the simple sentence. For example, we know that in binomial, there are two possible outcomes. But in binomial, they tell us that they will give you how many success, probability of how many success in the number, maybe 10 try or 20 try. But in Bernoulli, it's just only one try. It's two possible outcomes and only one try. So that shows that when you have two Bernoulli together, it gives you binomial. When you have more than one Bernoulli together, it gives you binomial. So binomial distribution is made up of many Bernoulli. Bernoulli is just the simplest probability distribution. Just as you know that it's just like as if I want to study only one person now. Only one person. Can you imagine? And I say, this only one person. I want to know your sex. If you're a male or female. That's Bernoulli. Because the only one trial, because only one person is only one trial. And there are two possible outcomes, either male or female, either yes or no. That's Bernoulli. But if by the time I go to another person, for that person also is Bernoulli, but when I add the two together, it's followed by binomial. So it's addition of many Bernoulli that you talk about, binomial. That is, out of these 10 trials, how many are success? But in Bernoulli, just one trial, what is the probability of success? That one trial. What is the probability that this person, only one person I see is a female? That is Bernoulli distribution. But if I am meeting 10 people, what is the probability that 6 of them will be female? That is binomial. If I'm meeting 2 people, what is the probability that both of them are female or one of them is binomial also? But once you are talking of only one, no, only one variable that has 2 possible outcomes, and it's only one person subject, that is follow Bernoulli distribution. And binomial, as we have explained it, and this is the common after in statistics, after normal distribution, which is a form of continuous probability distribution. This is the most, because normal distribution is the most popular distribution. After it, binomial is the next. So normal distribution is a form of continuous distribution, while binomial is a form of discrete. Because you see that for clinician, in fact, you may, if not because this normal distribution is the basis of hypothesis testing. In fact, in medicine, binomial will have overtaken normal distribution in popularity. They cannot be more popular than normal distribution, because normal distribution is the basis for hypothesis testing. The clinician like binomial distribution because they want everything to be in true form, either dead or alive, yes or no, treated, not treated. You know, they want to, if you bring blood sugar, the clinician want to know who is diabetic that I need to give drug, I need to treat, and who is not diabetic that I will not treat. If they say this is hemoglobin concentration, who is anemic that needs treatment, who is not anemic, that's it. They want to divide people into two. Who is hypertensive, who is not hypertensive, who is obese, who is not obese. You know, who is this, who has this, who doesn't have this. So, you know, clinicians like to dichotomize, and that is why the most popular type of analysis in medical literature is logistic regression, because logistic regression, the outcome is binomial. It's 2. Yeah, or yes or no? Yeah or no? So binomial distribution, look at the The efficient aggregate of multiple is aggregate of multiple Bernoulli random variable, as I've said. It shows the probability of every possible number of success in an experiment in which there are only 2 possible outcomes on trial. Now, if you look at the function here, you see number of trial, number of observed success, that's R. Number of trial is N here. That is, it has a fixed number of trial. See, out of 20 trials, out of 50, out of 400 trials, that will be N. That is the sample size. Number of observed success, that how many, like now, out of the 400, how many are female? R will be the number that are female. And see, the probability of the success is the P. This is the formula. N factorial over R factorial. So let me, when you go and look at it very well, the Poisson distribution, one thing, as I've said, that binomial distribution, if the sample size is large enough and you now do sampling many times, that is sampling distribution, not the real underlying data. There's no way a male female will follow normal distribution. It's categorical. But the sampling distribution is what can follow normally. That is, if I take sample now and say this is the very proportion of male or proportion of female, that value, if I record many times, it can follow normal distribution. If the sample size is big enough, it can follow normal distribution. That's any of these can follow normal distribution, or the discrete probability distribution. Poisson is a generalization of Bernoulli distribution. So as I said, that Bernoulli is the basis for all these discrete probability distribution. The Bernoulli distribution represents an event which can take on a value of 0 or 1 and has an implicit rate of occurrence of P. But Poisson distribution is something that can assume 0, 1 to whole number, because it's number of something is rate of something within interval of time or a space. Is rate, number of something, number of children, number of hospital admission, in a month, number of deaths in a year, all this mortality rate, number of deaths among mother, number of deaths among women of reproductive age, among infants, among neonates, all this number of, because you cannot say how many people there is 100.5 children died. Can you say that? It's only a whole number. You can, it's an integer. Integer in the next whole number. It cannot have fraction. Number of something cannot have fraction. So it's either 0, there's none, or 1, 2, 3, like that, to infinity, as many as. Okay. That is why Bernoulli is 0, 1. 0 just 1. It happened. It didn't have success. 1 is not the success. 0. Whereas for Poisson, it's number of something. It can be 0, it can be 1, it can be 2, it can be 3. Can you see now the difference? Even between Poisson, what follow Poisson and what follow binomial. Binomial, there are 2 possible outcomes. The here is the number of something. So while that is one of the reasons you cannot use the same logistic regression you use to model something that has 2 possible outcomes, to model something that number of many people make mistakes. And that was why our last training was on Poisson regression. You cannot use logistic regression to do that. You cannot use linear regression to do that also. So this, if you want to model what determines hospital admission, rate of admission, number of hospital admission per month, per year. If you want to cite an hospital now, a region, a private hospital, serious-minded people want to know, okay, all those other hospitals in that region, what is the patronage? What is the patronage? What are the factors that determine patronage? Before you go and cite one hospital in one place and you don't get any patronage. So for you to determine factors, to model the factor that determine patronage, the best will be Poisson regression. It's not logistic. You won't say, will they come, yes or no? Come to the hospital or not? Admitted or not? No. We're talking of admission rate now. How many admission rate, how many attend the hospital in a month, in a space of a month? So in that case, it can be 0, can be 1, can be 2, can be 3, can be whole number. So that type of variable follow Poisson distribution. And Poisson distribution is related to Poisson regression. And what you are seeing here is, you will see, depending on some factor, so that is the sample size, because this lambda here, which is the parameter for Poisson, is actually the mean rate, mean average. As the average number increases, the thing begin to follow normal distribution. It look like normal distribution. When the average number of that occurrence event increases, it will follow normal distribution. So all distribution tend to normal distribution when the factor are. Geometric distribution, the number of trial up to first success. I've said it. Theoretically, there are an infinite number of geometric distribution. Can you see now? Can you see infinite number of geometric distribution? That shows that there are factors that determine the value of any specific distribution depends on the value of the probability by P. Just like look at this one now. Poisson, there are many of the distribution based on the mean number of occurrence events. Just like you get to learn later, chi-square is a family distribution. There are many of them based on the degree of freedom. Help distribution is a family distribution. There are many of them. T distribution, there are many of them. It's the same thing with all these ones. So the three assumptions are in Poisson in geometric distribution. There are two possible outcomes for each trial, success or failure. So it's close, it's just like binomial, success or failure. How is it different? The trial are independent. Yes, in binomial, so the trial are independent. The probability of success is the same for each trial. The probability of success is the same for each trial. The here now you're going to have why geometric is different from binomial is that before you can get the first success, you have to make more trials. So usually model rare events, rare things that don't just happen. Success, the probability of success, you might have recorded failure, a lot of failure before success. Now, that shows that the sample size will be large. So if you look at the binomial, you have a fixed number of trials. Here you cannot have a fixed number of trials because you're actually looking for, you keep on try until you get the first success. So can you see how it's different? Look at the shape. Then negative binomial distribution. The word negative, you see why the word negative coming. Almost the same thing as binomial distribution, but the number of trials n is not fixed. In binomial, the number of trials is fixed. But here, the number of trials is not fixed. That shows that if I, for example, now, I say that you sample, you sample a particular population, you see, you look at the rate of occurrence of an event. In negative binomial, that one you have sampled, you have removed it from that population. So it's without replacement. Because if it's a replacement, the total number is still fixed. If you try again, it's going to be the population denominator is still the same, but here is reduced because the number is not fixed. Then a random variable y, the number of trials needed. Sorry, the thing just went out. I'm back. Yes. So here, the number of trials needed to make arrow success rather than the number of success. So you are not interested, here is not interested in number of success now. It's the number of trials needed to make arrow success. I think that's what we explain there in another way in that picture, in that graph. So this one is okay. Before, for you to, just like for somebody to, just like maybe somebody that is giving birth and it's time for you to have 2 children that stay, how many children are the person giving to back to? That type of thing follow negative binomial distribution. Here now is looking at, or even you can look at the logic behind maternal mortality rate. It can even made to follow negative binomial, because sometimes the logic behind maternal mortality ratio, not rate, is that for every one child, you see, you have one child that is alive, born alive. How many women die in the process? You know, maternal mortality ratio try to look at how many women die in the process of giving birth. The process is not just delivery, even having pregnancy, the exercise that lead to pregnancy. At the end of the day, maybe some women want to abort, the process they die, or after they aborted the infection they die, or in the process of carrying the pregnancy they die, or in the process of delivery they die, or after delivery they die. Whatever have to do with pregnancy up to puerperium, that is after even 42 days, 6 weeks after delivery, that has to do with pregnancy that can kill a woman. So how many women will die for us to have 3 children, or for us to even have 1 child? It can follow negative binomial distribution. That is what this one is saying here. Now, the random variable is the number of repeated trials. Are you seeing now? So what you are now interested in now is the number of repeated trials, now with number of pregnancy that have gone, number of pregnancy before even somebody also that is doing IVF, before you can get one, you can model it, because how many number of trial attempt before the person could get a child, or even get 2 children from the IVF. They follow a negative binomial distribution. You see, sometimes when you are analyzing, or you are trying to, your knowledge of statistics will bail you out. You really know when you see the situation, your knowledge, oh, this is the best way to model it, not just to be doing the same thing for everything, one big shoe size up. When you have understanding of what you are doing, different situation will present, you'll be able to know, oh, this is the right way to model it. Now, lastly, among the district we are talking about, district probability distribution is hypergeometric distribution. It's similar to binomial distribution. I said that the trial are not independent. So the trial now, just like the other one, this is the type of trial you also do with replacement. So it's independent mean that yes, that is why it's independent. It's not independent, but it's with replacement. That is, the probability of one trial affect the probability of the other trial. For example, now if they say that they put maybe 10 red marble and 5 blue marble and 3 green marble, making 18 in the pot. If you pick 1 red marble, if you pick 1 marble, what the probability is red? If it's picking without replacement, if you pick the first one, you will say, because the total is 18. So you got 10 all over 18, total is 18, but 10 of them are red marble. So it will be 10 all over 18. But by time, if it's without replacement, if you pick another one, it will be 9 over 17, because it's no more 18. So since there's no replacement, the probability of the first one has affected the other one. But if there's replacement, the probability of success in the first one has nothing to do with the second one, if there's replacement. And that's just the logic. So in that part, geometric distribution, they are not independent, just like in geometric, just like in binomial, where each success of each trial are independent of the other one. But in upper geometric, they are not independent. I think we stop here, so that by Tuesday, we'll look at continuous probability distribution. And also, don't be discouraged, because most of this one, the one you are most familiar with, binomial. But we try to also talk about Poisson. In some situation, Poisson distribution, most of the things people use binomial or normal distribution for follow Poisson, because the rate of occurrence of event, number of something, the rate, like all this maternal mortality, hospital admission. So then all these other one will be at the realm of theoretical concept for you now. But the more you get to know it, the more you appreciate it better. By Tuesday, we look at continuous probabilities where we talk about normal distribution. That one is very, very important because normal distribution is the basis for hypothesis testing. And we also look at, we look at, apart from normal, okay, maybe we'll just talk about the normal distribution at that time. The next one will now talk about the other continuous probability distribution like chi-square, t-test, and f-test. All of them, they are continuous probability distribution, but they are not normal distribution. But they tend to go to become normal when they are degree of freedom. So go and read it. Go and watch our video on degree of freedom. You'll be able to understand when we talk about degree of freedom. Okay, I have one chart here. Thank you, sir. Please, what is the difference between geometric and negative binomial? So it can be answered by going back to the geometric and negative binomial. When you look at it, we talk about geometric. Okay, describe the number of try up to the first success. Can you say up to the first success? Negative binomial. Talk about random variable, number of try needed to make R success. Number of try. So geometric, look at, as you are making effort, how many times have you tried before you get the first success? That is geometric. Negative binomial. For me to have 3 successes, how many try do I need? Is it clear? So that one is not the first success now. For me to have a particular number of success, how many try will I need? Well, that's negative binomial. In geometric, for me to have even the first success, how many try? Is it clear? At what point of data analysis do we come across the discrete distribution? Oh, great. Yes. Well, it's not as difficult as I understand. And thank God, when I was asking this question, you are joining us in this workshop we are doing. That's good. But I would have loved if you have joined along a better, notwithstanding. Go, you watch, you also subscribe, you are a member. Go and watch all those things. You get to appreciate it very well. So, for example, at what point do we need, what point do we come across the discrete distribution? It's not even at the inception. Even at the inception, even when you are doing your calculating your sample size, because the variable you are dealing with, the type of variable you are dealing, is it categorical? You know, categorical will follow discrete, while continuous, the quantitative will follow continuous. So even the type of formula you use, like now, if you want to, even if you discrete study, there's a tweak, there's a difference in the modification of the formula if the outcome is continuous or if it is discrete. Even if it is comparative study or any form of study, go on. If you watch our sample size determination, you're going to see it there. It's spread out there. So the issue of discrete is for discrete variable, categorical variable, the other one continuous variable. So even at this conception, then when you are what do I call it? Well, let me talk about leaf data collection. Okay, when you enter your data, so when you are now summarizing, the discrete is summarized as percentage. Though sometimes you can, for discrete numerical, you may still calculate mean, standard deviation, or whatever. That's it. But for all those categorical, either nominal or ordinal, is percentage. You don't summarize them with mean. The one continuous variable summarized with mean and standard deviation. When you are tabulating, is the discrete you can put on the table You cannot show continuous probability distribution variable on a table. If you put it on a table, you have already ranged it before you can put it. So then that is why for continuous, the only way you can show it is only graph. But if you want to show, like for the blood sugar now, you cannot show blood sugar on the table unless you have made up your mind to say, okay, I want to range it, any blood sugar between this and this. Because if you want to show blood sugar on the table, by the time you have 600 sample size, all of them give you about, maybe there are some may be the same value, but you have 400 over 400 different value for that 600. Will you show them on the table? It's not possible. Someone will be scrolling and say, this is my table of my blood sugar. It's not possible. It's the same thing for all continuous variables. The same thing for age. You will not go and put it. But you can now range it. Age less than this less than 20 years, 20 to 39, 8 to 39, 8 to 49, 50 and above. Now put it. And now put the percentage. But by doing it, even the age is a continuous variable. But that age range is not a continuous, it's a categorical variable. I don't know if the person that asked the question is able to get a clue from what I'm saying. So don't worry, you are coming for our workshop. Workshop is where we tear a lot of things down. You practicalize. You have some question. Okay, I'll just say, okay, read this thing. You have show all this thing. Click on this. You see the way it is. Yeah, I don't know if I have whet your appetite on that. Based on that question, say at what point of data analysis do we come across this discrete distribution? The table of sex, you see male or 60%, female 40%, is discrete probability distribution. The table of ethnicity, you put there and their percentage, is discrete probability distribution. All those tables you put, and you put percentage, they are all discrete probability distribution. Have I answered your question? Any other one? Any other one? Okay, there's no. Okay, if there's no other question, let me stop the recording.